Welcome to this live session for the lecture content of week 12 on this NPTEL course on hydraulic engineering. So this week's course was basically dedicated to the topic of uh, water wave mechanics. Okay, this was dedicated to the topic of water wave mechanics. Okay, this was dedicated to the topic of water wave mechanics. Now, uh, Uh, if you have gone through the lectures already, you must have understood one thing, that the basic or the fundamental idea of water wave mechanics begins with sorry begins with the linear wave. Okay, the fundamental idea begins with the linear wave theory. Okay, it begins with the linear wave theory. Now, as it begins with the linear wave theory, there is a very fundamental derivation associated with the linear wave theory, which make use of the unsteady Bernoulli's equation. So, in today's session, we'll try to see the derivation or the idea behind this unsteady Bernoulli's equation, how it is derived from, what is the idea, and then we'll solve a very simple problem, because already a lot of problems have been taken up. Already a lot of problems have been taken up. Already a lot of problems have been taken up during the actual lectures. So, okay, we'll try to see the derivation. Okay. Now, Now, let us begin with, okay, so unsteady Bernoulli's equation. In order to understand unsteady Bernoulli's equation, we will have to first of all discuss Euler's equation. So let us consider a fluid control volume as shown in this figure, whose dimensions are delta x, delta y and delta z along x, y and z direction respectively. This P is any arbitrary point whose coordinates are x, y and z. Okay. Now, the faces are marked here. You can see that Q, P, R, S, R, S, W, T, U, V, W, T, R, U, V, Q. Okay, so these are the faces marked like this. Okay. Now, acceleration field, you already know the acceleration field. So here I not like to spend much time in the acceleration field. But while we derive the Euler's equation, what is the basic assumption? We assume that the only forces that are acting on this fluid control volume are the fluid weight, that is the body force, and the pressure forces. So there are no other forces considered here. Okay, the only forces that are acting are the pressure forces and the gravitational force or the weight. Okay, now this point P, which I have already told you, whose coordinates are x, y, z. Okay, and at this point P, the velocity field along x, y, and z direction is given by u, v, and w components. Okay, now let the body force per unit mass at the same point is capital X, okay, capital Y, and capital Z. Okay, say are the body forces. Okay, say are the body forces. Now, if these are the body forces, then, and you can say that they are represented by certain potential. Okay, they are represented in terms of certain potential. So, by potential I means the force potential. I mean the force potential. Okay. Mm. Okay. Now, if we take the force balance for this control volume taking into consideration only the gravitational force and the pressure force, then from this acceleration field, from this acceleration field, you'll be getting a relation like this. Okay, from the force balance, from the concept of force balance, force balance, we are getting this. Okay, then they can be represented in terms of force potential. Now what is force potential? You will be getting a very good idea if you compare this with, see, if you remember, we have discussed something called phi, which is the velocity potential. So what is velocity potential? Velocity potential is something you can express, say, u direction, x directional velocity u as del phi by del x, where phi is a scalar function. So similarly, force potential is basically a function like this, which represents the x directional body force when its derivative with respect to that particular direction is computed. Okay, now if we use this expressions of u, okay, in terms of velocity potential and the body forces in terms of the force potentials in this equation, okay, the force balance equation, you will end up with something like this. Okay, now if density is constant, that is incompressible flow, and if we integrate this with respect to x, y and z, we will be getting something like this, where f1, f2 and f3 are constants of integration. Okay, and in short, means if you consider these three for any general direction, this can be written as this, which is the unsteady Bernoulli's equation. So this is the idea behind unsteady Bernoulli's equation. So please take few minutes and see whether you have understood it or not. See, so unsteady Bernoulli's equation, if we try to look at it step by step, what is the procedure? It is derived from Euler's equation. Okay, it is derived from Euler's equation. Now what is Euler's equation? It is basically equation, force balance equation, which takes into consideration only the gravitational force and the pressure force, which is the surface force. Okay, gravitational force plus pressure force. Now based on the force balance, based on the force balance on the control volume that we have chosen, we can write the force balance equation based on the acceleration field. Okay, now in that acceleration field, if you consider that the body forces, that is the gravity term here, is represented by some force potential, okay, is represented by some force potential, then and the velocity terms, that is u, v and w, are represented by the velocity potential, and if you replace this in the force balance equation that you have obtained for Euler's equation, or if you substitute it in Euler's equation, what will you get? Will you get the you will get a particular very complicated nonlinear form. Okay, you will get a particular nonlinear form, which is this, which is basically this. Now here if we integrate with respect to x, y and z, okay, if you integrate this equation with respect to x, y and z, you will be getting the unsteady Bernoulli's equation. So this is the idea. And one more thing that you need to keep into mind that whenever you are trying to solve problems related to water wave mechanics, you need to have a very good understanding of the wave tables. Okay, you need to have a very good understanding of the wave tables, how to uh, read the wave table. Okay, just like any other table, logarithmic table or trigonometric table or tables for your probability distributions, we have wave tables. Okay, so you should know how to read the wave tables. Now let us look at a problem, a very simple problem. A wave flume is filled with fresh water up to a depth of 2 meter. A wave of height 0.3 meter and period 2.2 second is generated. You have to calculate the wave celerity, group celerity, and energy and power. Please try this problem. See, in the question, see, this is the very famous relationship. What is the name of this relationship? See, it relates the D by L ratio with the deep water D by L0 ratio. Okay, now L0 is 1.56 t square, where t is the time period. So 1.56 into 2.2 square is 7.5504 meter. Then d by L0 value is 0.2649. Okay, now based on this value of d by L0 from the wave tables of SPM 1984, you can find the corresponding value of d by L. Okay, so the value of d by L is 0.2649. The value of d is already given to you. What is d? D is nothing but the freshwater depth of 2 meter. So the value of L is 7.1174. Okay, then celerity is L by T. Okay, it is the velocity, so distance by time, so wavelength by time period, 3.235 meter second. Group celerity, this is the standard equation, you just put all the parameters, you get the answer. The energy of the wave is gamma. Gamma is what? The unit weight of the water. Okay, and the power is Cg, where Cg is nothing but the group celerity. Okay, so this is a very simple example, but what I will try to suggest to here, you please try to understand the derivations and try to visualize this water wave mechanics part, because it is little bit complicated, and especially those who are from civil engineering branch, this part is a new addition. Okay, this part is a new addition, so you need to go through the derivations very carefully. Don't take consider the things uh, to be as it is, and try to go into the depth and look into the derivation. So with this we'll stop here. So this live session, sorry, this live session now ends, uh, and I hope that you have learned something, and all the very best for your exams. Thank you.